안녕하세요. Welcome back to Automatic Control Systems lecture. I am Professor Kalyana Veluvolu with the School of Electronics Engineering. In the last week, we discussed on root locus problems, various types of problems, on how to draw the root locus using the rules. This week, we are going to actually use root locus to understand how the design can be done, and moreover, we are going to study how the locations of the poles and zeros affect the root locus. So, let us proceed to the design with the root locus. Now, in the last class, we actually analyzed root locus for k, that is actually a multiplication factor. That means you should have the k here, or you can have h of s in the feedback. So, this is r of s and this is y of s. Now, this is the structure where we actually analyzed the root locus, formulated the rules, and then using those rules we construct the root locus. Now, we have a new scenario. What happens if k is not a multiplying factor? So, if k is not a multiplying factor, all our rules of root locus are not valid. So, suppose consider a system where you have this kind of structure where k is not even a multiplying factor, but k is 1 plus ks. So, there is a kind of expression, it does not actually look into any of the standard form. So, if the k is not in the form of a multiplying factor, we cannot use our rules of root locus. However, we have a technique where we can modify the system into the form suitable. So, we are going to change this system into a form suitable for the root locus. So, we know that the root locus depend on k into g of s, h of s is equal to 0. This is the characteristic equation. So, the root locus is dependent on this characteristic equation. So, what we are going to do is take this system transfer function. So, what we are doing is first formulate the transfer function, then formulate the transfer function, we can get the characteristic equation. So, the characteristic equation is given by 1 plus 16 into 1 plus ks by s square equal to 0. Now, once I formulate the characteristic equation, we can modify the characteristic equation such that it comes to this form. Now, if we actually write the characteristic equation, it is something of this form. So, what I am going to do is, I am going to actually take this characteristic equation, then divide with 16 ks. So, use this one and divide by this. So, I can write 1 plus 16 ks by s square plus 16 equal to 0. So, by doing this way, what I am trying to do is formulate into a standard form of this one. However, we should have k as a multiplying factor. So, but I have a 16k. So, I choose k dash is equal to 16k and then rewrite the problem. So, we can actually use k dash equal to 16k, replace 16k with k dash, and now this becomes our new transfer function instead of the earlier transfer function where we have 16 into 1 plus ks in the form of a where k is not a multiplying factor. By modifying, by choosing k is equal to 16k, I can actually write in a form suitable for our root locus. So, by doing that I can actually draw the root locus. Because this is in the standard form, I can draw the root locus. However, you have to understand the original k and the root locus k are slightly different. This is our root locus k, but this is our original k. So, when the design problem is there, like finding k, so you can find the k dash, that k1, with the any specific eta that is requested as eta is equal to for eta is equal to 0.707, take theta is equal to cos inverse eta 45 degrees, draw the line, the constant damping line, and it intersects at some point. So I want to find the actual k. So the actual k is product of the poles by product of the zeros. So I make the product of the values by connecting the locations of the poles to the point where the constant damping line intersects. So measure the values a, b, c, and you get k dash is b into c by a. Now the value you get is for this k dash, not for actual k. So what we need to do, change the value. So just modify the k and you can get the k value. So if you actually go through the problem, even when you have an expression that does not look like a standard form, you can change the characteristic equation. So we take this characteristic equation, modify this characteristic equation into the form suitable for root locus, just into this form, and then you can continue with the root locus. However, please remember that actual k is this k, but we choose a different k, that is 16k, and draw the root locus for k dash. So when you get the k dash from the root locus graph, you have to rechange for the actual k is divided by 16. So using this technique, although we do not have a standard form, we can continue with applying the existing rules and the existing frameworks for wide variety of problems. So if you actually look what kind of information we can get from the root locus, there is certain nice information we can understand about a system. We can understand what is the stability condition for k, when the system is stable, when the system is unstable, or the parameter to which the root locus is plotted. So the parameters can be design parameters, can be amplifier gain or something. So when you develop a real system, we have several parameters. So we can choose each parameter and then draw the root locus to find how the stability varies and how the properties varies. The second, so we can know the limits for the gain k from the RH criterion. So we know how the k changes the performance. When you change the k, the roots change. Roots change, damping changes, omega frequency, omega n changes, everything changes. Next, the fourth one, so we can also know for every k the characteristic equation, because you know the pole locations, you know everything, we can know the actual characteristic equation. Knowing the characteristic equation, we know everything about the system. Last, evaluation of performance criteria such as undamped, damped natural frequencies, damping ratio, and the transient response of exponential term. We can know everything from the root locus. Once we draw the root locus, it provides quite amount of information about how the system will perform with various kind of inputs and what are the various properties, and when the system is stable, unstable, everything we can know from the root locus. Next topic, we are going to actually use root locus to design. So generally the root locus is used to obtain a simple picture of the effect that gain k has on the position of local on the closed loop poles. So generally we can also use the same technique to design a controller. So we want to know, when I have a system, like let us say I have two poles, I want to know what happens to this root locus when I actually add a 0, when I actually add a pole, how does the root locus change? This is a very interesting topic. We are going to actually see how the system, how the root locus changes with addition of poles and zeros. So addition of poles. Suppose the controller introduces only poles. Let us say we only add poles. Then the closed loop characteristic equation will be of this form. So I choose a controller with this kind of poles, and then with the control transfer function you have the poles. Compare the root locus with GC is equal to 1, the addition of poles has the effect on the root locus. So, when GC is equal to 1 and when GC is equal to this transfer function, what is the difference? What happens when you add these new poles to the system? Adding poles, if you remember, adding poles means you are decreasing the stability of the system. When you add more poles, the root locus bends to the right. That is what we are going to see. When you add poles, the root locus bends to the right. So, the addition of the poles to the closed loop system results in a more unstable system. So, if we have a certain system, we keep on adding poles, the stability decreases. Next, let us go to a simple example to understand how the locations of the poles, the addition of the poles influences the system stability. In this example, I have 1 by S plus P1 as a controller, and let us say the original system has 2 poles. So, if you look at the original system, it has 2 poles. The locations of the poles, if you actually draw, are 0 and minus 2. 0 and minus 2, how is the root locus? You have 2 poles, 2 asymptotes, centroid will be in the center, simple, centroid is in the middle, 2 poles minus 90 and minus 90, so plus 90 and minus 90. So, it is very clear these 2 poles come, one goes this way, one goes this way. So, system root locus is actually in this way. Then I add a new pole 1 by S plus P1, then the closed loop system will have 3 poles. Now, let us see how the system affects. So, when I have 2 poles, like I told you, the 2 poles come together and they actually depart. Because of 2 poles, you have 90, 90, you get poles actually asymptotes going in this way. Now, when I actually add the poles with the root locus, when I add an extra pole, let us say I add an extra pole here, everything changes, because when you add an extra pole, asymptotes now become 3. With 3 asymptotes, you have 60 minus 60, 120. So, here 2 poles minus 90, 90, 3 poles 60 minus 60, 180. So, with 3 poles, I have this kind of scenario. You see the asymptotes bends to the right. When asymptotes bend to the right, what happens is you have this kind of asymptotes and this kind of asymptotes. When you have 3, these 2 poles actually break and go this way, and this pole goes to infinity. So, root locus, which is this one, bends to the right. When you add a pole, the root locus bends to the right. The actual selection of the P1 here, P1 is greater than 2. So, even when it is less than 2, it actually also provides a similar scenario. So, when you place the pole here, 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 anywhere, you will have the same root locus, but slightly modification in the gains or in the crossing of the imaginary axis. It depends on the actual locations of the pole. Suppose I take this P1, place in between, it may also give you a different effect or different graph, but it will be almost similar to this one. So, there is a simple exercise, if 0 less than P1 less than 2, so that the root locus is similar to 1. So, it will actually have a similar effect like earlier one. Now, let us take a new example here. In this example, instead of 1 pole, I am adding 2 poles. So, what happens when you add 2 poles? When the original system has 2 poles, so I get 90 minus 90, and then I add 2 extra poles, they become total 4 poles. So, when you have 4 poles, what are the asymptotes? 4 poles, 45 minus 45, 135 minus 135. So, you have the points here, you have the 2 poles here and the 2 poles here. So, because of the asymptotes, no zeros, these 2 has to break away, go in this direction, and these 2 break away and goes into this direction according to the direction of the asymptotes. So, when you have two poles, we saw that the root locus never crosses the imaginary axis. By adding one pole, the system which does not cross the imaginary axis crosses the imaginary axis. So, if you see the first case, when I only have two poles, this never crosses the imaginary axis. This system is stable for k equal to 0 to infinity. For any value of k, this system is stable. And then, when I add just one extra pole, the system crosses to the right hand side for certain value of k. That means the system which is stable for k is equal to 0 to infinity now becomes stable for only 0 to some k value. So, the system stability margin decreases. The system is only stable for only certain value of k. For some k higher than certain value, the root locus crosses to the right hand side. So, the system becomes unstable for some value of k. Then, when I add two poles, the stability margin even decreases. For example, two poles, system is stable for 0 less than k less than infinity. Three poles, for example, 0 less than k less than 55, some value randomly. Four poles, 0 less than k less than 10. So, that is how the stability changes. When you have two poles only, you have until infinity stability. When you have three poles, root locus bends to the right. So, for value of 55, system becomes unstable. For four poles, 0 less than k less than 10. The stability decreases. Okay. So, even you add the poles in between them or anywhere, the root locus will almost remain the same, except the locations of the centroid will change. We saw that addition of poles makes the root locus bend to the right, means system stability decreases with the addition of poles. What happens with the addition of zeros? So, opposite. With poles, stability decreases, with zeros, stability increases. Root locus that bends to the right with poles actually bends to the left with zeros. So, in this one, we are going to study what happens when you add zeros to the root locus. So, I have a system 1 by s into s plus 2. So, it's the same system we are studying, and then I add a 0. So, when I add a 0, earlier we have two poles, they actually go minus 90 to plus 90. Now, when I add a 0 here, I have two poles. One of the pole has to go to the 0 and the other pole has to go to infinity. So, these two pole comes, break away, break in, one pole goes to 0, the other pole goes to infinity. So, system which was also stable, but having the poles going to infinity for plus 90, minus 90 asymptotes, now bends to the left. So, you see it bends to the left. The system becomes more and more stable. So, this is for 0 that is greater than 2, but however, if you keep in between them, then it is slightly different. When you keep in between them, when the 0 is in between the two poles, this pole has to go to 0, the other pole has to go to infinity. This is because root locus only exists on a section when the number of poles and zeros to my right is odd. Here, to my right is 0 plus 1 0 plus 1 pole. So, you have two even, root locus does not exist here, and root locus exists here for all the region. So, if you keep a 0 in between, it will be slightly different. So, this scenario will actually tell us how the root locus behaves. So, this root locus is more stable than the previous cases. This is with 1 0. Suppose if we add two zeros, second 0 is here, root locus behaves in a similar way. Suppose I have two zeros, let us see a case. This is two poles, this is two zeros. Now, you can suspect asymptotes? No, no asymptotes, because m is equal to m minus n is equal to 2 minus 2 equal to 0. So, no asymptote. So, if you actually analyze, there will be one breakaway point on one break-in point. So this is breakaway, break-in, this goes to this 0, this goes to 0. So simple. So the system is never unstable. The other reason is the root locus will never go to the right hand side. Root locus bends to this direction. So that's with 2 poles and 2 zeros. So this is the best scenario we have. We can never have more zeros than poles. So that doesn't exist. For real system, this is wrong. N minus m is always greater than or equal to 0. So number of poles is always greater than or equal to m for real systems. So we can never have that scenario. What we have seen is we add zeros, system stability improves. If we add poles, system stability decreases. Now what happens if I add poles and zeros? Poles and zeros together give some interesting effect. So when I have a pole and 0, the actual root locus depends on where is the pole, where is the 0. The relative positioning of pole and 0 actually is important. So once for the same system with 2 poles, we add a pole and a 0, it depends on where it is. So if you see 2 scenarios here, when I place pole at 10, 0 at 2.5. So if you look at this graph, when you place a pole and a 0, that pole will go to the 0 and these 2 poles bends to the left. So since I place this pole close to these 2 poles, these are the 2 original poles, I place a 0 here, I place a pole far away. The pole is very far away. When this pole is very far away, like 10 times away, so the effect is very little. But still, because of the root locus structure, these 2 poles break away. The asymptotes is here because the centroid will be here. Because the difference between poles and zeros is 2, you have 2 asymptotes, 90 and 90. So these 2 poles break and actually go here, and this pole goes to 0. This is for the scenario when pole is far away, 0 is closer. If we reverse, or if I place this pole very close to this 0, that's going to be interesting. When I place this pole very close to the 0, what happens is this pole get attracted to this 0. So what happens is, since this 4 is very far away, these 2 poles come, break away, break in, this pole goes here, and the other pole comes here, again break away. So in this one, it's a bit complicated because you see that there are 1 breakaway, 1 break in, and one more breakaway. So you have 2 breakaways and 1 break in. So the actual scenario depends on the location of the poles. Okay. So this is what we call, in 2 cases we call lead compensation. Lead and lag are about phase of the signals. We will understand more about lead and lag compensation or lead and lag when we go to the frequency domain design techniques. But for the time being, you just remember it gives us a lead compensation. But the actual properties depends on the relative locations of poles and zeros, and it can be problem specific. We can't generalize. Now, for example, I place 0 far away, pole closer. Because the pole is closer and this 0 is far away, much far away, it has little effect. So it behaves like 3 poles. So because of that, the root locus bends to the right. And then asymptotes are here. So, and then because of that, our system still, which is not going to right hand side when you have 2 poles, now goes to the right hand side. System becomes less stable. Then in the other case, what happens if I have a pole and 0 slightly far away from the actual poles, or you see these 2 poles, this is the original poles, I place a pole and 0 here. In that case, these 2 poles acts like pole 0 cancellation. In that scenario, these 2 poles actually behave like earlier. So depending on the location and the choice of poles, where you keep the 0, where you keep the pole, the graph will change. Obviously, the properties also change. So these 2 above cases we call lag compensation, because the phase response provides you lag, and here it provides you lead compensation. So the controller, the addition of poles and zeros gives us some interesting properties of how it modifies. So, depending on our requirement for the controller, depending on what you need, you can actually design a lead or a lag compensation depending on the choice of the poles and location in the controller. So, this is like a controller. I have the system, I am adding a controller trying to change the behavior of the system. By adding this controller, I can actually control the root locus, change the properties of the root locus, and then you can get some interesting properties what you want. So, this is how the root locus gets modified by adding poles and zeros to a system. So, with this we are actually at the end of the class for week 11. So, for the week 10. So, in the next class we will be actually designing with the PID controller design. For this class, this is the last class for root locus. I would like to advise students to actually take a lot of problems on root locus, plot the poles and zeros, and then think how to draw the root locus. You do not need to solve all the steps, but instead take the root locus and think about what kind of steps are required and how to calculate them. Once you see the poles and zeros locations, you should be able to predict or guess how the root locus roughly looks. If you understand how the root locus will be, then solving the problem is very easy. One important point is, I have been teaching automatic control for the last 7-8 years, and most of the time I see in the examination papers, most students solve all the steps but cannot draw the root locus. This is because many students never practice. They read, they remember everything, but when they go to examination, they do not know which poles goes to which direction and which poles actually goes to which zeros. So, this, if you understand the root locus well, you will not make this kind of mistake. So, please practice a few problems. You do not need to solve all the steps, but guess the procedure and then understand with different configurations of poles and zeros how the root locus is. Even the GUI that I provided a link can also help you. Even on the internet, there are some nice softwares where you can plot root locus for wide variety of problems. So, thank you. This will be the end of week 11, part 1. Kamsahamnida.